Look around a crowded street or a busy office. It is organized chaos. You are looking at countless unique things interacting with each other all at exactly the same time. Whether it is a car, a coffee cup, or a pedestrian, every single item is a distinct object. It has specific physical traits, like its color or weight, and specific actions it can perform. If you need to build software to mirror this, say a global banking platform managing millions of distinct customer accounts, how do you write that without creating millions of separate, tangled lines of code? Writing traditional top-to-bottom procedural code breaks down at this scale. It scatters related data and actions, making a massive system impossible to manage. This is exactly the problem Object-Oriented Programming, or OOP, was designed to solve. It operates as a direct translation mechanism, allowing developers to organize digital architecture using the exact same logic that governs the physical world. This diagram illustrates the core of OOP. The top half shows what Java calls a class, a purely abstract blueprint. It is not a physical item you can drive. It simply defines the universal rules, dictating that anything built from this template must possess a color, a model type, and the ability to drive. To bring that blueprint to life, we use a constructor method and the new keyword, acting as a factory assembly line. This process is called instantiation. The constructor stamps out distinct physical objects, like objects 1, 2, and 3. Looking at this slide, we see 3 different mascots. Developers use overloaded constructors to create these variations. This allows objects to be generated with custom features right off the assembly line. A class represents the broad concept of a thing, while an object is the physical embodiment of that concept. We can apply this exact same logic to something completely digital, like a bank account, to see how the internal data works. This list outlines the instance fields, or states, of a bank account, giving the object its unique identity. Out of all these fields, the account number and current balance are core data points that must be securely stored. This next list details the object's behaviors, which in Java are called methods. These are specific actions the object can perform. For a bank account, the most critical actions are making a deposit or processing a withdrawal. These two sides are directly connected. When a behavior occurs, like depositing money, it directly alters the object's state by increasing the overall balance. Objects are active entities, not static data tables. Their behaviors constantly govern and update their internal digital identity. If that internal data is left entirely unprotected, the system breaks down. It would be catastrophic if any user could directly reach into the banking software and rewrite their own balance to $1 million. This table shows Java's access modifiers, the built-in security system specifying access rules. We make instance fields private, locking data away like a vault. To safely interact, we use public methods, acting like a bank teller. Looking at these first few lines of code, we use packages and the import keyword. This acts as a massive filing system, grouping thousands of related classes together so they can be easily referenced. Without access modifiers securing the data and packages organizing the structure, a complex software system would rapidly collapse into insecure chaos. By combining classes, objects, fields, and modifiers, developers have a complete toolset to translate real-world mechanics into clean, scalable software. Programming in Java is an act of digital architecture. You are meticulously recreating the physics, boundaries, and logic of reality inside a computer. What physical object in your room right now would you want to translate into a Java class first? Let me know in the comments below and subscribe for more deep dives into software architecture.